Enthalpy. What is it? In this video, we're going to be talking about enthalpy. Enthalpy is represented by the symbol H, and enthalpy is called the constant pressure heat. It's defined by this equation that you see here. Now, we talked about earlier internal energy as being delta E. So if we look at this equation, what we're going to see is that E is now going to be represented by the capital letter U. That's just the way it's going to be derived in this following form. So our main focus on this particular slide is to talk about what is enthalpy, what is it equal to. So we're going to go through a derivation here, and this derivation is not one that you're going to have to memorize or be able to do, but it's just something to help to try to understand where delta H comes from and what it's equal to. So our goal here is to be able to solve for what goes in that question mark. So we're going to use the differential equation, so that way we can solve for delta H. And so here we go. We're going to start off with H is equal to U plus PV. All right, remember E is equal to U. U is a representation of internal energy. P is pressure. V is volume. So we're going to take the total differential of both sides, and we get this form here where dH is equal to du plus dPV. Now, you cannot take the differential over two things at the same time. So what we're going to do is we're going to split up the dPV, and we're going to take the differential and keep the other one constant. So that's what we showed here. All right, so dH is equal to du plus dPV. So this is where we take the differential of pressure and keep the volume constant in this. And then here we keep the pressure constant, and we just take the differential of the volume. Recall from earlier that we talked about internal energy. Delta E is equal to Q plus W. So we take the differential of that, and we end up with du is equal to dQ plus dW. We're going to make a substitution here for du. So this substitution here is where we have the dQ plus dW is input here for du instead. So we see now that we have an equation dQ plus dW plus dPV plus nothing really changed. All we did was make the substitution. So we're going to define dW here. So dW is equal to minus PdV. So this is going to be substituted in for dW. And so we end up with this equation here. Now, dH now is equal to dQ minus PdV plus dP plus PdV. A little bit of algebra here, nothing major, just cancel out like terms. And what do we see cancel out? Minus PdV and plus PdV cancels out. So we're left over with dH is equal to dQ plus dPV. So now enthalpy, we talked about this at the beginning of the slide. Enthalpy is called the constant pressure heat. What's it mean to have constant pressure? Well, the pressure stays constant. So if you integrate over something that is constant, well, it's not going to change. 1 minus 1 equals 0. So what happens here in this part, this term cancels out because dP is 0, and anything times 0 is 0. So what do we get here? dH is equal to dQ. So we're going to integrate over the differential and both sides, and what we end up with, dH is equal to Q. This is important. dH is equal to Q. Earlier we talked about Q representing heat. So Q is heat. So that means that delta H is representation of how much heat is lost or gained by a system. So as we move forward, we are going to talk about enthalpy of a reaction. So enthalpy of a reaction is represented by delta H. We talked about delta H just a second ago in the previous slide where delta H is equal to Q. But if you want to calculate delta H, what we're going to do is we're going to have the enthalpy of the products minus the enthalpy of the reactants. So delta H can determine whether a reaction absorbs heat or releases heat. So delta H is used to describe whether a reaction is endothermic or exothermic. If your delta H is negative, your reaction is exothermic. Delta H being negative means that you're losing heat. So the negative sign means that you lose heat during a reaction. A fireplace is a perfect example because as you burn wood in a fireplace, it releases heat. So that's exothermic. Exothermic means it's going to release heat into the surroundings, so the surroundings themselves warm up. So it's a negative loss of energy from the system. So if you go the opposite way, where delta H is positive, that represents an endothermic reaction, and you're going to see that it's going to gain heat. Now, as the system gains heat, the surroundings will lose it. So if you have a thermometer in the surroundings, what's going to happen? It's going to go down. The temperature will drop for an endothermic process, and the temperature will increase for an exothermic process. That is a very important detail to remember. It's a very tough detail to remember because people get confused with exo versus endo. So they tend to think opposite. So be careful with that in the way you remember this. So as we look at a chemical reaction here, so you can see we have a combustion chamber here, the engine. So when we have 1 mole of methane gas burned, 890 kilojoules of energy is released as heat. Calculate the amount of energy lost when 5.4 grams of methane are burned. So in order to answer this question, we need to first make an inequality here. We need to try to understand what information is given and how we're going to use it. So the first thing here is that we are given that for every mole of methane burned, you're going to get 890 kilojoules of energy being released. So in this particular case, we're going to have negative 890 kilojoules per mole of methane, CH4. So notice that this negative sign is represented by releasing heat. So it's released. That's where that negative sign comes from. Now, it says calculate the amount of energy lost when 5.4 grams of methane are burned. So what we need to do now is make sure we get our grams of methane converted into moles of methane. So the molar mass of methane is 16 grams per mole. So we're going to take the 5.4 and we're going to divide it by 16, and we get 0.36 moles of methane. So we're going to take the moles of methane, and we're going to take this relationship that we just wrote up with kilojoules per mole, and we're going to use those two to calculate the amount of energy that's being released. So take the 0.36 moles, and we're going to multiply that by the negative 890 kilojoules per mole of methane. Notice that these cancel out here. So when you go through and you multiply that, you're going to end up with negative 320 kilojoules of energy. So that's just a simple problem where we take the amount of energy per mole and we use that as a conversion factor. So when we know the mass of a substance, we can figure out how much energy is going to be released or absorbed depending on the problem. So let's look at another example here. So here's an example where we take magnesium, we react it with HCl to form magnesium chloride and hydrogen gas. Now this problem tells you that the delta H is equal to negative 400 kilojoules. So that might be given to you, may not. In this particular problem, it is given to you. So that means that in this particular reaction, it was measured that 400 kilojoules are released from this particular reaction. So notice that the negative sign here tells you that this reaction is exothermic. Now, if we look at letter A, it says if 25 grams of magnesium react, how much energy will release during the reaction? So we want to take the mass of magnesium and we want to go ahead and convert that into moles. So always just get your mass converted to moles if you're given grams. So the molar mass of magnesium is 24.31 grams per mole. So all we do is just divide that out, and we end up with 1.03 moles of magnesium. Now the second thing we want to do is we want to come up with a relationship and with relation to the amount of energy that's released during the reaction per mole of magnesium. So if we look at the balanced equation, we see that there's 1 mole. So that means for this particular reaction, the delta H is negative 400. So that means that for every 1 mole of magnesium, you're going to release 400 kilojoules. All right, so take this moles of magnesium, they're going to cancel out here, and we're going to multiply by the negative 400, and we end up with negative 412 kilojoules of energy. So what that means is that since this is an exothermic process, it's going to release 412 kilojoules of energy based off the amount of magnesium that was present. So in part B, it says if 910 kilojoules of energy released, how much hydrogen gas were produced? So to do this particular problem, we're given 910 kilojoules. So this is sort of working backwards from the problem that we just did. So we still need the conversion factor. Now in this case, we're going to be looking at the delta H on per mole of hydrogen gas. So if you look at the balanced equation, we have 1 mole of hydrogen gas there. So we're going to divide it by negative 400 kilojoules per mole of hydrogen gas. All right, and that's going to give me 2.275 moles of hydrogen gas. Now they say they ask how much hydrogen gas is produced. They don't really specify in moles or grams. So in this particular case, we're going to say what mass. I'm just going to change it here. What mass of hydrogen gas was produced? So we need a molar mass of hydrogen gas. Well, the nice thing about this is the molar mass of hydrogen is 1.008, so that's going to be 2.016 grams per mole. So we're just going to multiply this together here, and we end up with 4.59 grams of hydrogen. So from 910 kilojoules of energy released, we can figure out how many grams of hydrogen gas was produced. So this is just a couple examples of how we would use the delta H for reaction.